Hello everyone. So let's keep on talking about some linear algebra concept. Specifically, let's remember the concept of eigenvalues and eigenvectors. So for an n by n matrix A, scalars lambda and vectors v, okay, here is different than 0, satisfying AV equal lambda v. They are called eigenvalues and eigenvectors of A respectively. So we can think about A being a linear transformation between an n-dimensional vector space to an n-dimensional vector space. And the vectors V, the eigenvectors, are the vectors that keep the direction of this transformation, just change the magnitude of this transformation by lambda, but it keeps in the same direction. Yeah. So this set of distinct eigenvalues, denoted by sigma A, is called a spectrum of A. So geometrically, AV lambda V says that under the transformation by A, eigenvectors change only on magnitude or sign. So if lambda belongs to the spectrum of A, if and only if the matrix A lambda I is singular, and it happens if and only if the determinant of this matrix is equal to 0. The characteristic polynomial for A is given by this, and its degree is n. So let's see a little bit closer why we have to have that the matrix A minus lambda I should be singular. So we have here AV equal lambda V for V different than 0. Okay, we want to find the vectors that satisfy this relation, the vectors V and the lambdas, scalars lambdas, the scalars lambda, such that it happens for V different than 0. Then we have here A minus lambda I, the identity matrix, n by n, V equals 0. So this will happen. So because we are searching for non-zero V's, this will happen if and only if A minus lambda I is singular. So the question is why this happened. So let's think that we have some matrix B, B that goes from some space n-dimensional V to V. Let's say, for instance, that is the Rn, for example, and we have here B x equals 0, and then here we have that x belongs to Rn. So Bx will be on the image set of this transformation, and if B is non-singular. It means that B is invertible, that we can find the inverse of B, non-singular. So for non-singular B, the only solution for this system is x equals 0, which is a vector of Rn, okay? Then the question is why again? It doesn't explain what we are trying to prove here or to understand here. So all of this comes from the null rank theorem. So there is a theorem that says that the dimension of the rank of B, it's equal, the dimension of rank of B plus the dimension of the kernel of B, it's equal the dimension of V, which is n here. Yeah. So which set is that? So rank of B is the vector space or the subspace that is spanned by the rows or the columns of B. There is a theorem that says that the rank column is equal to the row rank, which means that the space, the dimension generated by the columns of B is equal to the dimension spanned by the rows of B. And the kernel of B are the set of all the vectors that are under the transformation of B goes to the 0 of the subspace. So the kernel of B, it's defined by all the, let's call vectors W in V, this V here, yeah, that such that B W equals 0. Okay. So now going back to our system here. If our matrix is non-singular, it means that the dimension, saying that a matrix is non-singular means to say that you can find the inverse, that the inverse exists, which means that all the lines or all the columns of the matrix B are linearly independent. So it means that the dimension of rank of B here would be equal n. So it would imply the dimension of the kernel of B should be 0. So the only element that is there is the null vector. So here in this case, again, we are searching a non-zero vector such that this happens. So the only way to find non-zero vectors that satisfies that are a solution of this system here is when this matrix here is singular. And for this happening, we have that the determinant of A minus lambda I should be equal 0. Okay, I just put this theorem that where I got it from this link here. You can search on internet also for, I think it's rank rank nullity theorem, something like this. Okay, and now we have some exercise here that I'm going to let as homework. So find the eigenvalues and the eigenvectors of the matrix. So we just need to first calculate the lambdas such that this equals 0. So you calculate the characteristic polynomial for the matrix A. You will get a second degree polynomial, then you get lambda 1, lambda 2, that are the roots of this characteristic polynomial. And then you first take lambda 1, and then you do A minus lambda 1 I V equals 0. Then you're going to get the first eigenvector, and then you do the same to the other eigenvalue. Okay. Now let's remember about some definitions that we are going to use in this course, actually in this class. So the definition of a sequence. A sequence is an infinite list of terms y0, y1, y2 until infinite. Yeah, infinite terms. A difference equation expresses a relationship between terms of a sequence given by this notation. So when we saw this cell division model in the beginning of our class, it was a difference equation. I was already using the term. So we have some examples here. So in this first and the second, we have, so here is a linear difference equation, and it's first order. We are going to see this further. Okay, y is like this, and here is a nonlinear, and also first order. Okay, let's go for more definitions. So let's start to talk about the difference equations. So a general mth order homogeneous linear difference equation with constant coefficient can be written in this form. So we have an and yn plus 1 until a0. So here the term yn relates with the terms until it's related to m terms, so it's mth order. For instance, if we have some difference equation that's like n plus 2 plus 2yn plus 1 plus 3yn equals 0. So we can see that this term here is related, or this term here, it's related to the past term, what happened in the past term, and it also depends on the term before n plus 1. So this one would be said a second order difference equation. In the non-homogeneous linear difference equation, it's written in this way. Observe that the only difference is that homogeneous it's equals 0, and the non-homogeneous has something different than 0 here, okay? And it could be also a function of n. So let's look at some examples. On the first one, we have this n here. It shouldn't be on top. It should be down here. So it's like this, okay? So this is a linear. So why it's linear? It's because the y something, they are relating to each other in a linear way. We see that we have here, even though some nonlinear function, but this function is not a function of yn or so on. Here is a function of, let's call r of n. So it's a function that only relates to n. So this is a second order. How we can see that? So each term here, it's related to past two terms, okay? So this is second order and this is linear. And the other equation, the next one, it's first order, so the n only related to n plus 1, but now it's nonlinear because you have that way yn square is a function of y of n. And on the next one is fourth order, and it's linear. Again, I have a mistake here. This n is floating. It should be here, a sub in this. So yeah, so this one is also linear because again, here what we have here is only a function of n, doesn't involve y. And the next one, the last one, is third order, and it's nonlinear because here cosine of yn, it's a function of yn, okay? And it's a nonlinear function of yn. Yeah, and here I go back to our motivation in the beginning of the class. So we have the cell division model that's given by this. and so it's a first order and it's linear. Yeah, here again I just find the solution. So I suppose that the solution is like this, and then I substitute on the equation. Then I find that lambda is equal a, and we can show that our c will be y0, which is just m0 in the previous notation. So the solution is like this. Okay. Now we are going to think, and if we had some non-homogeneous solution. So in this case, we just add here something like this, n. We could consider this n in our cell division model, that we have some cells that are being added in the system, but they are independent of the others, or that instead of each cell, the mother cell splitting and then it doesn't exist anymore, we just have some bursts like this. So the cell gives birth to two, but this cell here doesn't die, it keeps on existing. Okay, that would be some explanation for this n in this model. So here is again first order linear difference equation and non-homogeneous. So what would be now the solution of this equation? So the solution of the non-homogeneous equation will be the sum of the solution from the homogeneous and a particular solution. So the homogeneous the solution is mn, it's equal an times m0, and the solution of the non-homogeneous will be the solution of the homogeneous plus some particular solution. Okay, and it happens because for a linear equation we have the linear superposition principle, that is, the sum of solution is also a solution. So let's try to solve this problem. So we suppose, as hypothesis, by the way that the function that's here, we suppose that our solution looks like this. Our particular solution looks like this. Yeah, I also noticed that I'm using different notations. So yn, it's sometimes also called mn, which is the number of cells in the nth generation. Okay, forgive me for that. So we suppose that our solution looks like this, and what we do, we substitute here. Okay, so if yn is equal this, so yn plus 1 should be a n plus 1 plus b. Okay, so it is yn plus 1 minus a times mn or yn. Okay, and then it should be equal n. And then we can rearrange the terms. So we have here a n. Now let's arrange this by what's multiplying n. So n will be multiplying a, and from the second part will be multiplying minus a times a, and it is equal. Okay, let's just get some other slide to do this. Okay. So we have here that our system is yn plus 1 minus a yn, it's equal n. And as hypothesis, we have that the particular solution of this system, because of this side, should be also a polynomial. So an plus b, a first degree polynomial. And we substitute in here, so we have that a n plus 1 plus b minus a. So here it is our yn plus 1 and a times an plus b. It should be equal n. So here we have our yn. So let's put in terms of what's multiplying n and what's not multiplying n. You will see why it makes sense. So in the first we have a, and for the second we have minus a, and then the rest would be a plus b minus ab equal n. And then we can rearrange it to look a little bit better. So n a times 1 minus a plus a plus b times 1 minus a equal n. So on the left side we have some first degree polynomial on n, and on the right side also some first degree polynomial on n. And for some polynomial to be equal another, so if we have some p1 of x equal p2 of x, some polynomial 1 equal another polynomial, it so the polynomial here is first degree, so we have some a1 x plus b1, it's equal a2 x plus b2, and this will be equal for every x if and only if a1 equal a2 and b1 equal b2. So that's what we do here. So for this to be true, we have that a 1 minus a, so there is a 1 here, plus 0, right? The free term is 0, so a should be equal 1, and also this term here should be equal 0, so a plus b 1 minus a should be equal 0. So then we get some linear system on big A and big B, and we solve this system and get A and B, okay? And the solution, you can do it yourself, and we get this solution here. A should be equal this and B should be equal that. So the solution of the general system should be the solution of the particular one. So here is missing an n. So the solution of the homogeneous plus the solution of the particular one. So the homogeneous, it is yn equal a n y0. The 0 is down, and plus the solution of the particular one. Now we are going to talk about the second order difference equation, which is homogeneous case, which is just n related to n minus 1 and n minus 2. And considering that the general solution should be like this, and substituting on the difference equation, we will get a second order polynomial. So you can do it yourself by, so if xn is equal this here, you can just say that xn minus 1 it's equal c lambda 2n minus 1, and also xn minus 2 should be c to n minus 2. And then if you put on evidence c, so big C, here you will have c lambda 2 n minus 2, and then you are going to see that this part here, yeah, sorry, I'm on the wrong equation. So here you will have some c times lambda n multiplying this, so big C lambda n, and equals 0. Because you are searching for non-zero solution, the only possibility will be that this term here it's equal 0, okay? Then you have a second order polynomial, second degree polynomial, and this polynomial, the roots of this polynomial will give you lambda 1 and lambda 2, that they are called the eigenvalues of this equation. and you can have two real solution, and if this happens, then the general solution will be like this if they are different from each other. But if you get some single root, then you want to have a linearly independent solution, and for having that you need to put this n here in order to have a linearly independent solution. Okay, and it could also be that you have some lambda 1 and lambda 2 that are complex, and the complex roots of a second degree polynomial always comes in conjugate pairs. So the lambda 1 should be something like this, and the lambda 2 should be something like this. And the general solution would be like this. Also the sum of it. But it's also possible that you transform this complex solution to look in a real way. Let's see something like this. So I just say here now what I said before. So the second order difference equation have two solutions, and the sum of the solutions is also a solution. We also want that this solution is linearly independent set, and when we have real roots lambda 1 and lambda 2, they can be equal or different. For equal roots, it is not possible to have a linearly independent set on the same way for different roots. That's why we write the solution by putting this n here in order to have a linearly independent set. And for complex roots, we can just write it using the De Moivre formula. So first we write our complex number that are a plus bi and a minus bi, and the solution will be something like this, which doesn't give us not so much knowledge about the behavior of this solution. And then we make some coordinates change for the polar coordinates. So we write that a and b are given by this, and then our r and our theta, anyway, it will be given by this. Okay, you can just draw your complex plane and see how these are related. So originally you have here the real part of lambda 1 and the imaginary part of lambda 1, and originally a is the real coordinate, so you have here is a, and let's say that b is here, and this is our vector in this coordinate. And then you can just say that instead of looking for a and b like this, you just look for the r and the theta here, and then you get the polar coordinates. And using the Euler's theorem, we can summarize this relation. So a plus bi can be written in this way, using r and theta, and also a minus bi. And our complex number, I written in this way. And now we use the De Moivre's formula, which is just how to calculate the exponential, like when you have some exponent on your complex number. So a plus bi to the nth. Then you substitute the polar coordinate here, and then our r, that's a scalar, gets something like this, and then our last shape of our complex number will be something like this. So we just see that n, the power, when you make a power of n to a complex number, you are just rotating on the complex plane. And then we look to the solution of our difference equation of second order. So the original way is like this, and then if we just substitute this relation that we found before here, you to get something like this, and then you can just write everything that's related to cosine together, and then everything that's related to sine together, and then you can just define our b and b1 and b2 constants here. Okay. And then we say that xn has a real part and imaginary part, because it's multiplying by I here. And we can just define again our un and vn, and our solution will be something like this. Okay. And then it can be proved that the real and the imaginary parts of this complex solution are themselves solutions. So because of the superposition principle, the sum of solutions are a solution. The sum of solutions are a solution itself. So un is a solution for this equation, and Vn by itself is also a solution of this system. And it is then usual to define a real valued solution by linear superposition of the real quantities un and vn. Okay, it is because un and vn, they are elements of the vector space, and here I times b2 is just a constant, a scalar. Okay, so you can just see that this sum here is just a linear combination of the vectors un and vn. Yeah, and more about the complex roots. So the complex eigenvalues, are lambda 1 and lambda 2. They are associated to oscillatory solutions. These solutions have a growing amplitude if r is bigger than 1, and decreasing amplitude if r is smaller than 1, and constant amplitude if r equal 1. The frequency of the oscillation depends on the ratio b divided by a, which is our theta. So related to our theta, because theta is defined by the arctangent of b divided by a. So why it is, when we have complex eigenvalues, why it is associated to oscillatory solutions? It is because of how the solution looks like. We have, for instance, un. Let me just go back. Yeah, so un is r to n times cosine of n theta. So it is, as we change our n here, we will have some oscillatory behavior happening here, and our r here will dictate if this oscillatory behavior it is increasing or decreasing. So we can say that if r is bigger than 1, then the amplitude will increase. It will be still oscillating, but then increasing. So our solution will have a behavior like this, increasing. Okay, the last one didn't increase. Okay, so it will be okay. Of course, I draw it as continuous, but remember that we are on discrete time. Okay, time 1, time 2, 3, 4. And for r smaller than 1, our solution will be decreasing amplitude, so it will start big and then become smaller. And if our r it's equal 1, so here r equal 1, our solution will have oscillatory behavior, but with constant amplitude. And the frequency of oscillation will be like related to also to the peaks of this oscillatory behavior. So the distance between two peaks is the wavelength, kind of. Yeah, I think that's the name used, the wavelength. And it will be related to theta, that is which is by definition related to b and the ratio b divided by a. Okay. And then here I yeah. And then here I have an example. I have some second order difference equation here, and then I find the characteristic polynomial, and then I get complex roots, and then I get my a is equal 1 and my b also equal 1, and then I calculate my r and I calculate my theta, and then I write my real valued general solution, just using our construction in the slides before. So here it's our r, here, yeah, not with n, so this pi divided by 4 is our theta. Yeah, so this is how we write our real valued solution. Okay, let's make a pause now before starting to talk about system of